All right, so let's dig into regression trees a bit. Regression trees are one particular method for non-parametric regression. And the reason we're going to talk about them is because, like linear regression, it's a relatively simple test bed where you can understand the ideas of how these things are fit. And however, they are also the basis of more advanced methods, also like linear regression, which is the basis of things like neural networks, logistic regression, same thing. But decision trees are the basis of methods like random forests, which we've already seen in action, and another method called boosting. So it's important to understand them. And the overall picture is actually the same as we've already done for linear and logistic regression. This is how they're fit. You pick a set of candidate functions. You pick a way to grade how well a candidate function fits the data, and then you develop an algorithm that's going to search all the candidates and find the one that's the best fit. So candidate functions. We already saw for linear regression, we're considering all lines. But of course, all lines, that's a bit limiting. Why don't we consider instead all staircase functions? So why staircases? And a staircase, I could be going up, it could be going down, it could go down and up. What we mean is a function that is piecewise constant. And maybe let's say it has less than d number of steps. So these kind of like flat bits here. Sure. So the reason this might be nice is because we can actually fit kind of arbitrary relationships. The trend doesn't need to be monotonically increasing or monotonically decreasing. It can go down, it can go up. Moreover, if we let the number of steps be very, very large, we can actually approximate basically arbitrary curves, right? If we just make these very, very, very small steps, we can fit almost anything very, very well using functions that look like this, like these staircases. So that's pretty reasonable. Now, why are they called trees? They're called trees because although we can visualize the function like this, we can also visualize the function like this. So let's say over here I have these values x1, x2, x3, which are the places where the function goes up or it goes down. And then we have these the flat parts. So I can say if the input is greater than x2, it's somewhere over here. It's in this bucket. And then if for the values that fall in this bucket, if they're less than x3, they're in this bucket, and the output value is this number. So here I'm drawing it like this. So let's say it's on the bigger than x2, so it's going to go into this bucket. And here, if it's less than x3, if it's less than x3, I'm going into this bucket. And so this is the value that I'm predicting. So here the colors represent the value of the output of the function. So these like darker colors are higher values, and the lighter colors are lower values. So I can represent this function like this, where I just have what are the buckets that I can fall into. So here there's 4 buckets, and these buckets are sub buckets of the buckets up here, and those are determined by these split values. And then within each bucket, we just have a value. Once you fall into a particular bucket, everyone in that bucket gets the same prediction, right? That's why the function is flat in those regions. So we can represent it like this. And this is a tree. If you want to see that, flip it upside down. This is the root, and these are called the leaves. These final buckets are called the leaves of the tree. And so this is a tree in the kind of computer science sense, where their trees are upside down. And if we were talking about functions that have a certain number of steps, well, that's equivalent to saying how many leaves there are, because each leaf is one of these flat regions. It's one of these buckets. So if we have 4 leaves, then there's kind of 4 flat regions and the jumps between them. So this is actually a parametric function. If we consider the number of leaves as fixed, like for let's say staircase functions that only have 4 steps, or 4 flat regions, I should say. If we fix that, then there are actually this is actually a parametric function, the same way that linear regression is parametric. You have the slope in x1 and the slope in x2, and then the intercept. So those are the 3 numbers you can play with. Here, for this function class, we have 1, 2, 3, 4, 7 numbers that we can play with. And they are the values that the function has in each of the leaves. So is this value high, or is it low, or where is this flat region? And then also what are the values of these cut points that define where these different buckets are? So is there a wide bucket, a narrow bucket? So these x1, x2, x3, and then these 4 numbers are the parameters of this function. All right, that is the set of candidates. Now the next thing we need is a way to grade how well they fit. And here we're going to keep it simple. Let's not reinvent the wheel. We'll use MSE. We've already seen this. We look at the residual and we square it and we take the average across the data. We can go with that. You can use other functions as well, but let's just look at that for now. And now the last part, which is the hard part, we need to find a way to figure out what these thresholds and what these leaf values should be. How do we find this? So again, let's just consider the case where we've decided we only want a tree with 4 leaves, and we just now want to know, well, where should we put the splits in the data, and what are the predicted values in the leaves? Well, let's simplify. So let's imagine that we had already picked the splits. So x1, x2, x3 are known. Those are fixed numbers. How do we then pick the best leaf values? Well, this is easy. It's just the group means. So let's say we have this bucket here. And in this bucket, we have these 2 data points. I'm just trying to find a number. So if the prediction is going to be a flat line that minimizes the mean squared error. So graphically, so these are the residuals, right? So I want to minimize the squared residuals across all lines. So I could have also chosen this line, and in which case the residuals would be like that, right? Obviously, that's worse. This line gives me smaller residuals. And in fact, the value that gives you the smallest residuals is, so this value here is the average. So this is the number, I'll just say number in leaf. Number in leaf over the sum of the values in leaves of the outcomes. So it's just the average outcome in the leaves. That's going to be your best leaf value. So if the buckets are already fixed, all you need to do is just compute the group means in each of these buckets and say that's the predicted value. You can't do better than that in terms of mean squared error. And you can prove that if you want. You can ask ChatGPT basically to say among constants, the minimizer of mean squared error is the sample average. Now the problem is that we have not actually fixed. We don't actually have the buckets. They're not known, right? So how do we pick the best splits? Should x1 go here, or should x1 go over here, or should I first split by x2, or how do I figure out what the structure of this tree is? Even if I know how to figure out what values to put in the leaves, how do I figure out the structure? And you may think, I don't know, gradient descent worked for linear regression, gradient descent worked for logistic regression. Does it work here? Actually, no. So if you'll recall, the idea of gradient descent is that we tweak the parameter, or conceptually, we tweak the parameter value a little bit, increase it or decrease it, and we see if the loss went up or down. And if the loss went down, we go that direction. Whichever way makes the loss go down, we tweak the parameter value in that direction, and then we keep repeating. So for example, if we changed x2 a little bit, we lowered it, and the loss decreased, we would keep lowering it, okay? But here you can see what happens. Let's consider this function, and let's say, okay, what if we tweaked x2? We lower x2 a little bit. Now we get this function. The question is, did that change the loss? Did the loss go up or down? If you look carefully, you'll notice the loss doesn't change. Why? Because the loss is determined based on these residuals, right? So for this function, the residuals are like that. For this function, same residuals, right? No difference. No difference. So there's no difference in the loss between x2 taking this value and x2 taking this value. It doesn't matter. And so by changing x2 a little bit, the loss doesn't change. There's no way to know which way we should move x2. So that sucks. So gradient descent actually does not work for picking the splits in regression trees. So the naive approach would be brute force. You try all possible different combinations of x1 and x2 and x3, and you'll actually notice that you don't need to, for example, you don't need to try x2 here. You can just try x2 on this side of this data point or on that side of this data point, because we know that the loss will only change when x2 crosses one of these data points, because then the residuals will actually be different. But you still need to try a lot of different combinations of x1, x2, and x3 in order to find the best regression tree. And in fact, if you have many leaves, or the dimensionality of your data is very high, this is just computationally not practicable, even on modern computers in a lot of cases. And so we come up with this alternative approach. here's the workaround. Let's just pretend, like I know I want to fit a tree that looks like this with 4 leaves, but let's forget about the 4-leaf tree. And let's pretend I only want to fit a tree with 2 leaves. So there's just going to be one split. And I just want to find the value of that split. Well, now this is not so bad because I just need to try every possible split value, but there's in this data set, there's 1, 2, 3, 4, 5, 6, 7, 8. So there's only eight values that I need to consider, and I can just try x at this value. I can try x at that value. I can try x at this value. And at this, so I can just try it at those 8 different cut points and see which one has the lowest loss. And notice that at each one that I'm trying, the leaf value is changing because it's going to be the group mean of whatever values are in that bucket according to this split. Okay, so let's say I've determined that this one is the best. It has the lowest MSE. Now I'm going to fix that. So I'm going to make that a hard split, and I'm going to forget that I ever chose that. I'm going to say like this was given to me from on high. Now I will consider, well, okay, so I have this bucket over here, and I have this predicted value, but maybe I should make this into 2 buckets. How should I split this in order to get 2 buckets to minimize the MSE? So I can consider splitting here, and over there. And then I do the same thing for this side. I can split this into 2 buckets. And what you might notice is that when I'm considering how to split this bucket, all this stuff doesn't matter. And when I'm considering how to split this bucket, all of this stuff doesn't matter. So I'm doing the same thing in this bucket as I did in the original, when I was considering the original data. It's actually the same code I can use to try all of the different splits. I'm just using it on a subset of the data instead of on the full data. Same here. I'm just now considering finding the best split in this subset of the data instead of in the full data. So that's what's going to give me this value here. So I've split this bucket into 2, or I split this bucket now into 2 buckets, and I can do the same thing over here. Split this bucket into 2 buckets, and find those values, and now I'm done. So now I've found my 4 splits, and I've taken the group means in each of the resulting buckets to give me the values, and this is my final fit. This algorithm is called recursive partitioning. It's recursive because I'm applying essentially the same code to split. At the top we have the bucket with all the data in it, and we split it into 2 buckets. And then we apply the exact same algorithm to find the best split within each of those sub buckets, and so on and so forth. So it's recursive. And it's partitioning, obviously, because we're splitting these buckets into smaller buckets. Now, this algorithm is not optimal. It's greedy. When we picked this first split, we were pretending that all we were looking for was a tree with 2 leaves, and we were trying to get the best 2-leaf tree. But then we fixed that value, and then we went on and split these values. So as a result, the tree that we get, this value is optimized to make the best split up here. It's not necessarily optimized to give this the best tree once we've also made these splits. So if I've made these splits, I could then go back and find a split up here that might actually be better than the one I originally found. But we're not going to do that, because otherwise we could keep going round and round and round and maybe never get anywhere. So this does not produce the best possible tree necessarily. It's not optimal. However, in most cases, it's very good. It is good enough. This is different than linear regression. In linear regression, the search algorithm actually gave us the exact best line out of all possible lines. It has the lowest training error out of all possible lines. For regression trees, we're not going to necessarily get the tree that has the lowest possible training error. There are combinations of the splits and the leaf values that might be better than the one that you get in terms of training error, but it's very hard to find them computationally. And so I'm actually just going to skip over here. So here we have the set of candidate functions as trees. We have mean squared error to grade, and we're using this recursive partitioning algorithm, which is now no longer actually giving us the empirical minimizer among the set of trees, but it's giving us something that's good enough. So it's a bit different. But you see overall the kind of roadmap is the same. For every machine learning method, it's the same. So you have some set of candidate functions. Sometimes it's kind of implicit, but in this case we can write them down explicitly. We have a loss, and we have some way to pick the model that gives us the best value of that loss. Sometimes that's an exact algorithm, like gradient descent, that will give us exactly the minimizer. Sometimes it's approximate or greedy, like recursive partitioning. So here we're always kind of trading off the performance for what's computationally feasible. Now, this also extends easily to multiple predictors. So all these examples, we're just using x1 here, right? But now we have x1 and x2. What I'm showing you here is a top-down view of the prediction function. So it's still actually at like steps. It's just steps that are now in 2D instead of or in 3D instead of this like one predictor. So again, the colors indicate higher up versus lower down. And you can see I can also represent this in the tree format. So here I first split x1 is less than or equal to a. So a would be this value right here. This would be the a value. And if that is true, then we end up in this bucket, which is these two buckets combined. And then depending on this b value, if x2 is greater than that or less than that, then we end up in one of these two buckets, which is either here or here. So that's a tree in multiple dimensions. In terms of the algorithm, how do you fit this? It's exactly the same. It's just now that when you're doing this search for which value where should I split, you need to look at splits in one dimension, but you also need to look at splits in the other dimension. So I could consider splitting x1 equals a, x1 equals b, x1 equals c. I should also consider splitting at x2 equals a, x2 equals b, x2 equals c. So instead of just 3 splits to evaluate, I maybe have 6. So you end up with a lot of splits to evaluate. And sometimes there are little hacks that people use, and they'll randomly select a subset of features. Let's say if you have 100 features, at each leaf, you'll randomly pick 10, and you'll pick the best split in one of those variables among those 10 variables that you randomly picked. So there, definitely, you're not getting optimality, but it turns out it's pretty good in general. So this is the kind of function fit that you get when you have multiple predictors. So let's play around with this. We already have this. Let's fit a regression tree with depth 5. And we want to predict just using age. Here's the magic. What is it called? Oh, it's called decision tree. Decision tree is another word for a regression tree. It's a slightly broader term, actually, because a regression tree is usually specifically referring to the case where you have a continuous outcome, whereas decision tree maybe can refer to the case with the binary outcome or categorical. So I need to change that. And how do I set the depth? Well, that is where you have these hyperparameters. So if you look up decision tree, you will see you have these extra arguments that you can set. So these are the hyperparameters. Engine, by the way, most of the methods, actually I think all the methods in tidy models have this engine argument. This is how you tell it what package you actually want it to use under the hood. So if you look at linear rate regression, you will see the default engine is LM. It's actually just calling LM. So, but for decision tree, it's going to call this package called rpart, which is a package in R for fitting regression trees. But you can also use these other packages. The reason for that is that they may be slightly faster. They may have slightly different parameters that you can pass. But tidy models just abstracts away all those complications and says, I'm just going to pick which package to use. The defaults are usually fine. And it maps on whatever hyperparameters you pass here into whatever they're called in these different packages, because they may be called different things, but that does not matter. So these are the parameters, hyperparameters. So tree depth is how you tell it essentially how many splits to do. So in our examples here, we are looking at trees of depth 2. So we had 1 split and then 2 splits. So now we're kind of two layers deep in the tree. I could have also kept splitting. I could have 4 or 5 layers. So now I'm going to ask for about depth 5. And the way that you set that here is saying tree depth is equal to 5. Now I'm also actually going to set this cost complexity parameter to 0. And the reason is that this thing, we didn't talk about this, but a lot of tree algorithms, they will fit the tree to the desired depth, and then they will prune the tree back because they're trying to avoid fitting the data too closely. So they'll say, actually, when I did this split, I only increased the MSE by a very small amount. So I'm going to not do that. And I'm just going to pull it back. So this thing kind of controls to the extent to which that is happening. So I'm going to set it to 0 so that it doesn't happen at all, and we really just get the full depth of the tree. All right, so I think that's it. So let's do this. And we can get the predictions. Yeah, sure, let's look at the MSE. Okay, so here the MSE is worse than it was before, but that's because we're only using age as the predictor. So we're kind of kneecapping ourselves here. So let's make some plots. Let's put this, let's call this spreads. Okay, so yeah, there's our test error. And plots. Let's go to ggplot. So let's plot age versus charges. Let's put a little scatter plot of the, this is all testing data. So the, let's make them kind of transparent so there's not too much noise. And then, what is it called? .pred. I think that's it, right? Oh, there we go. That doesn't look right at all. What's going on? Did I not redo it? Oh, yeah, why? All right, there we go. Sorry, guys. Need more coffee. So here's our prediction function, and here's our data. Now, this is actually not totally accurate picture of what the prediction function looks like because it's being evaluated at the test points, and then geom_line is just basically connecting the dots. So you can do geom_step, and then this is what it actually will actually look like. You could also get really the best way to look at the prediction function would be to generate a sequence of ages that's just, like 20, 21, 22, 23, so on and so forth, and then get the output of the function and then step between that. But anyways, you can see here that we do have a this kind of stepwise function that is being estimated, and this is the relationship that it's finding between charges and age. Now let's also add smoker as a predictor. Easy, okay? And now here, let's add color. So now you see actually what's going on is that this group of people down here, these are the non-smokers. And then most of these people up here with much higher charges are the smokers. And so the regression tree has actually learned that there are sort of different relationships going on. And I bet you that what has happened is that the tree basically looks like the first split are they a smoker or not? And if they are a smoker, then you go into this sub-regression tree, because you can think of a regression tree as like a depth 5 regression tree is just 2 depth 4 regression trees glued together at the top. So then there's going to be like a depth 4 regression tree for just the smokers and one for just the non-smokers. And actually, we could probably look at that. So what is this? M. So there it is. This is our regression tree. This is the output that we get. So indeed, yep. So the first split, so we have root, which has everybody in it. And then the first split is smoker equals no or smoker equals yes. So the 800 non-smokers, that's these red dots, all go into one branch. And then if we scroll down here, yeah, here's the 200 smokers go into the other branch. And this is like the top split of the tree. And then you can see after that, all the splits are just based on age for both of them. So it's just like 2 age-based regression trees glued together at the top with smoker. And you see these are the little stars are the leaf values. So these are like the flat bits, the values of these flat bits. That's pretty cool. All right, so let's look at if we include everything. Okay, so here you can't really tell, but it's doing very well in prediction. You can't really, this person has, like maybe this person has, what are the other values in this? yeah, we got sex and BMI and children. And so maybe these variations have to do with BMI because we're not plotting that, but the prediction model has it. So this plot is not really meaningful anymore. The reason I wanted to do this is actually, let's just get rid of that. Let's go back to this. Is because I wanted to see, so when I train using all of the predictors, I got my predictions, I have the useless plot, and then, okay, here's my my test error. Let's do RMSE again. Test error is like 5,200. That's actually lower than the regression or than the random forest that we were doing earlier, which is not often that happens. But that's pretty cool. And if you remember that the linear regression was like 6,600 or something like that. So this regression tree is much better than that as well. So in that example that we just saw, the regression tree is pretty good. In fact, better than the random forest. But in general, that's not actually the case. And regression trees can be very sensitive to the training data, especially this usually happens when you have a lot of predictors, like let's say 50, 40 predictors, okay? And the reason is that you have this like greedy algorithm. So oftentimes if you have a slightly different data set, it's from the same population, but it's a different subsample. In that subsample, it's gonna look like the best initial split is some other variable, some other value. And so you can get a very different looking regression tree, even though it was fit from pretty similar data from the same population. So they can be very sensitive and the predictions can kind of fly around a lot. Not always, but sometimes. And so this is a problem that people noticed for many years in the, I guess, early 90s. And then somebody came up with a clever idea. Actually, I should have a slide on this guy, but he's also a Berkeley guy. Leo Breiman, EI. This guy. So he, I don't want to attribute it entirely to him, but I'm pretty sure he did basically, he's mostly attributable. The random forest algorithm is mostly attributable to him. And he also did work on CART, which is this basically decision tree thing that we were talking about before. The first algorithm goes to this guy, actually, at IBM Research. And then this, Leo Breiman did kind of like more of the theoretical work. Good to know. Anyways, this guy's a Berkeley guy. He was here for a very long time. And a big impact in the field. Anyways, the idea is, what is a random forest? The idea that these people had and that the Breiman kind of formalized was that you can, instead of just fitting a single regression tree to the data, if the problem is that the data are random and the regression tree that you're going to get is going to be kind of random, and it might be a bad random, it might be a good random, you can split your data up into lots of different subsamples, so like bootstrap subsamples, and you can fit, let's say 100, so you have 100 different subsamples of your data, and you fit 100 different regression trees on all those different subsamples. They're going to be different, those regression trees. But then you can average the predictions of all of them, and the average predictions will be much more stable than the predictions of any single regression tree. So it looks like this. So instead of having this one regression tree, you're going to fit 4 or 100 regression trees. Actually, kind of the more the better. And all of them are going to be different. So you can see, because this is a different subsample that it was trained on, maybe the first split is the same, but after that, it looks different. And so these are all quite different. But if you average 100 of these things together, the function that you're going to get is going to look like this. So again, here light is the lower values, darker is the higher values. And what you can maybe see from this is that it's still this kind of piecewise thing, but it's much smoother than the original functions. And so oftentimes you're going to get a nice, more smoothed out fit of your data. And this is what a random forest is. So it's a forest because, well, you have like 1,000 trees. Okay, so forest. Random because each tree is fit on a different random subsample of the data. Random forest. And this is actually the kind of output you get. We saw this way at the beginning. Let's do my little demo. That's what we see here. So this function, this is kind of smoothed out by R a little bit, But the reason it looks kind of chunky like this is because it's all these piecewise constant regions. There's just a whole bunch of them, and then R in this visualization is kind of like gluing these things together. So you're not really seeing the pieces, but you can tell that's very different than this, which looks very smooth. So here we have these like little pieces because this is an average of the predictions of like 1,000 regression trees. So that's very cool, I think. And that is the idea of a random forest. So now you know, and you can use that.